Okay, so what we're looking at today is we're looking at two-way tables. And we have like one of them on what we did Friday, I think. And I'm sure you guys have seen them before in other contexts. But specifically what we're looking at with respect to two-way tables is conditional probability. Although every single problem on here is not a conditional probability problem. So first thing you want to do when you see a two-way table, first of all, there's two different types of two-way tables. There's two-way frequency tables and there's two-way relative frequency tables. Here's the difference. Let's say that particular table right there. First of all, let's go ahead and total our rows and columns. Okay, this is marbles in a bag. So altogether there are 6 large marbles. Altogether there are 20 small marbles. Altogether there are 10 green marbles, and altogether there are 16 blue marbles. So the grand total number of marbles in the bag can be found by either adding the row totals or adding the column totals. Either way, you should get what? Yeah, I almost said 36 there too for a second. 26. So your grand total goes down there in the corner. And if you wanted to, you could like make it where you extend, where you just extend the table so that you have boxes out there, and then 26 would go down here. But this is a frequency table because it's telling you how frequently you find that particular item. You find, you know, the frequency of blue larges is 4. Now, if we were to do a relative frequency table, what we would do is we would take all those numbers and divide them by 26, because that's what is the frequency relative to the whole. Okay, so like large green, there are 2 large green, 26 marbles. So that particular entry, instead of being a 2, would be a 0.08. Okay, so let me just green, blue. Let's do this. Okay, so 0.08, 10 out of 26, and 8 out of 26 for the rest of that column. So this is now this is where things get interesting. 8 out of 26 gives me 0.307, which would round to 0.31. But if I added 0.31 and 0.08, I would get 0.39. 10 out of 26 is not 0.39, it's 0.38. So sometimes you have to tweak these just a little bit because of rounding. Okay, so like I think I would say probably instead of 0.31 here, I'm going to leave it as 0.30, and that way I've got 0.38 here. Then 4 out of 26 is 0.15. And let's look at what 12 out of 26 is and what 16 out of 26 is and see if those are going to need a little tweaking or not. Nope, 0.46. And 0.46 plus 0.15 is 0.61. Although look at that, that would round up to 0.62. So actually, we need it to be 0.62. So let's make this, which one is closer to rounding? Let's make this 0.16. And then this is 0.62. These two need to add up to 1 because that's 100%. This one down here, the same spot that had everybody in the frequency table, has to be 1 in a relative frequency table. Okay, because 1's like 100%. Okay, and then we've got, let's see what's going to happen here with adding 0.08 plus 0.16 is 0.24. This is going to be 0.76, so that would work okay. I don't have to worry about the fact that they're going to be a little bit off. And usually it would just be off by 100. And so you can kind of make the call as to how you adjust that a little bit so that it all works. You want the sum of every row to be over here. You want the sum of each column to be down here, and you want those to add up, both of them. 0.24 plus 0.76 equals 1. 0.38 plus 0.62 equals 1. Now, when you have it in a relative frequency table, that's what this is, relative frequency, because it's relevant to the whole. When you have a relative frequency table, or relevant, then what you have is basically the probabilities of finding each one of those things out of the whole. In other words, the probability of drawing a green large marble is 0.08. The probability of drawing a blue small marble is 0.46. But these are with respect to the whole. So this is, in other words, if I just randomly pick a marble out of all of them. Okay? It's not conditional probability, which is when I say, if I know I get a large, what's the probability it's green? Or if I know I got a green one, what's the probability it's small? Those are conditional. But we're just talking about probability out of everything, not out of a condition, not narrowing down the sample space just to one type. Okay? And that's what you find in a relative frequency table. You can, even the totals work that way. In other words, if I reach in randomly, what's the probability of drawing a large marble? 0.24, same as 24%. If I reach in randomly, what's the probability of drawing a blue marble? 0.62. Okay. However, a lot of times we don't necessarily go to the point of finding this, because we can still, easily find that out of this. If I want to know the probability of drawing a small marble, 20 out of 26. It's not a hard division problem, right? So a lot of times we use just the plain old frequency table, but I wanted you to know that the relative frequency table has decimals instead of numbers. Frequency tables have a count. It's like counting up how many items. So if you're asked how many items, you're being asked this. If you're given this and asked how many items, then you would have to know what the total was, and you'd multiply that decimal times the total. Okay, so frequencies of marbles in a bag are shown on the table. Find the probability of drawing a small marble. Well, that would be 20 out of 26. We actually just talked about that. 20 out of 26. We're going to do it as a decimal. So 20 out of 26. It's 0.77. I think we got 0.76 in our relative frequency table. That's okay. If I'm doing it from here and I'm dividing, I'm going to go ahead and go with 0.77. That's what this. Why was it different here? Because I had to round. Okay, that's the only thing. All right, now this is conditional. This is where it gets into not out of the whole. This is where it gets into I can't just look at this and figure out one of these numbers, because those numbers are all out of the whole. This is saying what's the probability of drawing a green given that you got a large. So it's green out of large. So the total for large, remember that second thing is like your bottom number of the fraction. So the total for large is 6. Number of those that are green is 2. So it's 0.33 or 1/3. The hardest thing about these can be wording. Sometimes you have to really be careful about the wording to make sure you understand whether it's asking you for a probability out of everything or a probability out of a specific smaller group. Okay, so be very aware of that. A town planning committee is considering a new system for public transit. Residents of the town were randomly selected to answer 2 questions. Do you work less than 5 miles from home? And would you use the new system to get to work if it were available? The results are shown in the table below. Okay, if residents work less than 5 miles from home, okay, what that does right there, if residents work less than 5 miles from home, that narrows down my sample space. That says I'm only worried about the people who work less than 5 miles from home, so I'm not doing a total of the whole table. I'm doing a row or a column total depending on which one shows residents less than 5 miles from home. I do need to go ahead and do some totals here though. So less than 5 miles from home, yes, that's this column. So 24 plus 44 is 68. So this is saying out of those 68 people, what is the probability that they would use the new system? So that's the yeses out of the 68. So that's 24 out of 68. And that's 0.35. All right, let's go ahead and find the rest of our totals. 32 and 20 is 52. 24 and 32 is 56. 44 and 20 is 64. And that gives me 120 total. That's how many people were polled. Okay. If residents are willing to use the new system, okay, that's narrowing it down. Only out of people who are willing to. So that means the people who said, yes, I would use it. So that's 56 people. Out of those 56 people, what is the probability that they don't work less than 5 miles from home? So out of those 56 people, no, I don't work less than 5 miles from home. It's 32. So 32 out of 56. These can be easy, but they can also be easy to get wrong if you're not careful. Okay? If you're not careful that you read it and make sure you understand exactly what's being asked, it can be easy to get the wrong answer or do the wrong thing, do the wrong division. The table shows the results of a poll of randomly selected high school students who were asked if they prefer to hear all school announcements in the morning or in the afternoon. Okay, I'm going to let you guys try these two. These are written in that given that format with the vertical line. Find the probability that they said morning given that it's an underclassman, or find the probability that they said afternoon given that they were an upperclassman. Okay, I went back and I underlined these a little harder because I wanted to make sure you saw that I'm going to use this as a comparison. This part right here is exactly the same as doing this right here, saying given that such and such. So this could have been phrased that way. It could have said, given that a resident works less than 5 miles from home, what is the probability they would use the new system? Or what is the probability someone doesn't work less than 5 miles from home, given that they're willing to use the new system? When it gets a little bit more complicated is when they kind of integrate that phrase in there. And I don't know if this is going to sound complicated, but sometimes it's just easier to overlook if I say, what is the probability that a resident who's willing to use the new system lives less than 5 miles from home? If I say that a resident who's willing to use the new system, it's almost like what? Is it a who is willing? It's not a preposition phrase, is it? But it's one of those descriptive phrases, okay? If we were diagramming sentences here. What is the probability that a resident who is willing to use the new system? That's the part that narrows it down for me, okay? So this is find the probability that they said morning given that it was an underclassman. There are a total of 26 underclassmen. 8 of them said morning, so 8 out of 26 there. Find the probability they said afternoon given it was an upperclassman. There's a total of 24 upperclassmen. 10 of them said afternoon. So those are my fractions I'm using. Total of 50 people surveyed. And I'm getting 0.31 for this one and 0.42 for this one. Now, if they had said, now probability, remember, probability is always a number between 0 and 1. You can write it as a fraction or a decimal, but 1 means absolutely certain and 0 means definitely not going to happen. If you were asked for percent, you'd multiply by 100. If it had said What percent of students who were surveyed are underclassmen who prefer morning or whatever? Actually, that's not the way that would not phrase that way. What percent of the underclassmen, what percent of the underclassmen prefer morning? That's what this is. This is what percent of the upperclassmen prefer afternoon. Now, what I said earlier, this is when it gets a little tricky. If I said, what percent of students surveyed are underclassmen who prefer morning? When I say what percent of students surveyed, that means out of everybody. So you got to look for those little clues. Do you mean out of everybody? Do you mean just out of this group? That's what can be tricky about this. Questions on this page before we go on? The table shows the results of a customer satisfaction survey for a cellular service provider by location of the customer. In the survey, customers were asked whether they would recommend a plan with the provider to a friend. Find the probability someone said yes. That's implying out of everybody. So let's go ahead and get our totals columns and rows. I always check my own math, making sure that these add up to the same thing. And they do. So the total number of people surveyed is 150. Find the probability that someone said yes. That's 116 out of 150. .77. Find the probability they said yes, given that they live in Arlington. Okay, so that's 40 out of 58. Are the two probabilities the same? That's a big no. Questions there? Okay, I'm going to pause and let you guys catch up, and then go ahead and try number 10 and 11. I know I just said catch up. Catch up. Catch up. I still see a bunch of people working, so I'm going to wait. If you're going on to 12 through 15, feel free. But we're going to do those together, so then you'll know if you were right. Okay, let's talk about Roberto. Roberto is the owner of a car dealership. He is assessing the success rate of his top 3 salespeople in order to offer one of them a promotion. Over 2 months for each attempted sale, he records whether the salesperson made a successful sale or not. The results are shown in the chart below. In the cart below, no. In the chart below. Find the probability of being successful given that you're Becky. Becky has had 12 attempts. 6 were successful. So 6 out of 12, which is 0.5. Let me go ahead and do these. Okay. Find the probability of being unsuccessful given that you're Daryl. Okay. Daryl has had 15 attempts. 9 of them have been unsuccessful. So that is 0.6. Okay. We'll come back to that one in just a second. Mrs. Kohler surveyed 430 men and 200 women about their vehicles. Of those surveyed, 160 men and 85 women said they own a blue vehicle. Okay, so now the first thing I need to do is finish the chart. Okay, so I've got 630 total. This is 245. 160 from 430 leaves me with 270. 85 from 200 leaves me with 115. No, feel free to jump in if I do my mental math wrong. 250, 380, that seems right. We're good? Did I do everything right? Okay. All right, so if a randomly chosen person is a man, so that just narrowed it down. So now we're talking only out of the men row. So out of 430. What is the probability of that person having a blue car? 160. So 160 out of 430. 37.37. Okay, what is the probability of not being blue? A car not having a blue car. So that means out of everybody. So not blue is 385. Out of everybody is out of 630. I get 61.61. 61% of people do not have a blue car. What is the probability of being a woman if we know you don't have a blue car. So that's out of 385. Probably being a woman is 115 out of 385. Bless you. Is 0.298, so 0.30 to round it. And this is what? This is the intersection symbol, right? Intersection symbol is and. Remember, the union symbol is or. So this is the probability of being a man and having a not blue car, which means these people right here. So that means those people right there out of everybody. So 270 out of 630. Should be 0.43, I think. I reduced it in my head, so let me go back and make sure. Yeah, 0.43. Okay. Questions on any of those? Last thing we're going to do this here together, and you do have a Google form homework to do that I think you'll find pretty straightforward. The only thing I'm worried about is how the form works. So let me know if you're having problems. Let me know if you have suggestions if you're having problems. I don't know. I think I've set it right. We'll see. Figure out who he should give the promotion to here. If you already have, then just hold off till the rest of us do. Who should get the promotion? Becky should, because people who name Becky are awesome, because that's my name. Okay, no, because Becky's success rate is 0.5. Raul's success rate is 0.44. Daryl's success rate is 0.4. So it's very easily mathematically justifiable to give the promotion to Becky. Questions on any of this? Alrighty. So go ahead and check out that Google form, and tomorrow we will review, and Wednesday is quiz. Okay, so the other thing I mentioned on Google Classroom, to make sure you guys hear it too, is since we're reviewing tomorrow, make sure tonight that you go back and look at what we did Thursday, Friday, see if you have any questions over that, see if you have any questions from anything before that on probability, and we should be good. We should be good to go, and you can ask your questions tomorrow. Thank you for coming. Aria?